Okay, so good afternoon students. We'll continue with our third session on field effect transistors. So very quickly we'll just go through the slides of what we had covered in our previous two sessions. So it was BJT versus FET, then primary differences between BJT and FET. Okay, so we had just gone through these things. JFET symbols, then a water analogy which actually described the functioning of a JFET in a simplistic way. Then the construction and the characteristics of JFET. Okay, so we are aware of this particular structure now, and we also know the characteristics of a JFET. Okay, so when VGS is 0 and when VDS is having some positive value, then what will be the behavior of the current. Okay, so we have gone through these things already. Yes. Okay, so just to reiterate, well, this region is called as linear and the next region is called as saturation level. Okay, and the voltage that actually differentiates between linear and the saturation is called as pinch off voltage. Okay, and pinch off is that particular stage within JFET where the depletion regions tend to touch each other. Okay, although there will be a small gap always present. Okay, so that is the status of the pinch off condition. Okay, so yes, so this diagram clearly depicts the pinch off condition. Beyond pinch off condition, the device acts as if it is a constant current source, okay, because of the saturation part. Then when VGS is being reduced, the pinch off occurs earlier, okay, more quickly when compared to the situation when VGS will be 0 volts. Okay, so that's the entire graph of the output characteristics of a JFET. Okay, so as VGS increases negatively, the pinch off occurs more quickly, so that the resulting current will also be lesser, right? So we'll be getting lesser and lesser current. So we have gone through these things in the previous class. Then the P channel device, the working is similar to that of an N channel device, the only difference being the polarities as well as the regions. Okay, so this is the characteristics of a P channel JFET. Okay, all right. So coming to the transfer characteristics. What does the transfer characteristic actually mean with respect to a JFET? Okay, so before going through those things, let us very quickly try to understand the two types of characteristics exhibited by transistors. Okay, transistors exhibit two types of characteristics. Two types of characteristics. The first one is called input characteristics, which we also call it as transfer characteristics, and the second one is output characteristics, which we also call it by the name drain characteristics. Okay, so far we have seen about the output characteristics or the drain characteristics. Okay, we haven't yet seen how the input transfer characteristics of a JFET looks like. Okay, all right. What about the relationship that actually exists, okay, between the controlling and the controlled parameters in the case of a BJT as well as in the case of a JFET? So the first expression actually corresponds to that of a BJT. Okay, so let us first look at the BJT, then try to compare it with respect to a JFET. Okay, so BJT is a 3-terminal device, emitter, base and the collector, and BJT is a current controlled device. Current controlled device. Okay, so when we say current controlled, which current actually controls which current, right? So the base current which is the input current, usually controls the collector current, which is the output current. Okay. Then what about the relationship between input current and the output current? Well, it says that a linear relationship exists between the collector current and the base current IB. Then mathematically, how can we represent it? The output current can be represented by this particular simple expression, okay, which says the collector current IC is nothing but a function of base current IB. Okay, so in terms of the proportionality constant, we just mention it as beta into IB. Okay, so usually beta is a very large value. Beta is a large value. Okay, so that when a small base current will be multiplied by beta, you will be getting large output current IC. Okay, so beta is a constant here. Now the point is, between IC and IB there exists a linear relationship, okay, which is extremely important. Now coming to a JFET, okay, a JFET. Well, it is being told that a non-linear relationship exists between the drain current ID and the gate to source voltage VGS. Okay, is that correct? Yes, it is correct. Why? Because the JFET current is mathematically given or expressed by the equation called Shockley's expression or equation. Okay, so this is the Shockley's expression which gives the formula for the drain current, and it is expressed like this: ID is equal to IDSS, where IDSS is the drain to source current during saturation, okay, multiplied by 1 minus VGS upon VP the whole square. So since JFET is a since JFET is a voltage controlled device, and the voltage that actually controls the JFET is VGS, right? So because of which VGS is being termed as control variable. What about the constants? Well, IDSS and VP stands for pinch off voltage. Both of them are constants, right? But still, how do we say that a nonlinear relationship exists? Well, nonlinear relationship exists due to the square term involved here. Okay, so that now all we can say is that ID is proportional to the square of VGS, okay, which is completely non-linear, right? So let's try to understand it further. Okay, so how to obtain the transfer characteristics? Obtaining transfer characteristics. Obtaining the transfer characteristics. Well, transfer characteristics can be obtained by two methods. One is the mathematical approach, and the second one is graphical approach. Okay, mathematical approach is slightly complicated, but it is more accurate, but slightly complicated. Okay, what about graphical method? Graphical method is very simple but approximate. Okay, well, we'll try to look at the second one, which is a graphical approach. Okay, mathematical approach is also simple, okay, but when compared to the graphical approach, it is, I mean, the number of steps involved are little more, that's it. Okay, well, let's look at the graphical approach now. How to obtain the transfer characteristics from the output characteristics. Okay, so the heading is obtaining transfer characteristics from output or drain characteristics. Okay, so for that we'll have to draw the drain characteristics first. Okay, so let me draw that drain characteristics. We are comfortable with the drain characteristics now, right? Because we have seen it many a times. So this is IDS, drain to source current, and drain to source voltage. When VGS is 0, we will be getting maximum current. So initially the current will increase linearly and then it will just saturate. Okay, so this is called pinch off. Further, if VGS increases in a negative way, say from 0 to -1, pinch off occurs quickly and the current will be reduced. Okay, it is flat. Okay, further, still further, okay, we'll be getting lesser current. So this is for -2, -3. Okay, maybe when VGS is equal to -4, both the depletion regions may appear to be joining each other, so that okay, the current will be almost flat and 0. So this may be -4. Okay, so this is during pinch off with respect to VGS. Right, now how to obtain the transfer characteristics? See, this was the drain characteristics. Okay, now using the drain characteristics, we will have to plot the transfer curve or the transfer characteristics. The transfer characteristics. Okay, and transfer characteristics is always a graph of output current versus the input voltage. Right, so let me just draw it and represent the axis first of all. So the axis is again the vertical axis is the same, IDS. What about the horizontal axis? It is the input voltage. The input voltage is VGS. Right, so now I'll have to plot the graph. So let me just select a different color pen. Yeah, okay, so how to plot it? It's very simple. Graphically you will have to just extend the corresponding voltages onto the axis. What does that mean? See, when VGS equal to 0, okay, you just try to extend that line. Okay, so when VGS is 0, okay, so this is the point. So now you have got the first point, right? Then the second line. By the way, I'll have to denote the markings on the VGS. -1, -2, -3, -4, -5. Okay, so let me stop here. And on the drain characteristics, let it be some feasible values, 5, 10, 15, 20 and so on. Okay, so when VGS is -1, then I'll have to just extend the line horizontally, and on the transfer characteristics just extend the line where VGS is -1 vertically, so that the point where they meet I'll have to join it. Okay, further -2, I'll have to do it the same way. Okay, sorry for these two lines. Okay, these are unintentional, but due to the problem with the pointer of the pen, okay, I am getting those lines. Okay, so you can just ignore these lines. Okay, so we have got one more point. Similarly, when VGS is -3, we'll be getting another node or point. Okay, finally when VGS is -4, VGS is -4. See, now I'll have to just join the points. Okay, so this is how the graph looks like. Now since I have drawn it manually, it may appear as if it is linear, okay. However, it is not linear, it is a perfect non-linear graph. I'll just draw it how it actually looks like. It looks like this, okay, in reality if you plot it on a proper graph sheet. Okay, so this is perfectly a non-linear graph, okay, because IDS is proportional to VGS the whole square, okay, due to this term, right. So in the next slide it is very clearly represented, okay, in a proper graph, right. So here you can just observe it, okay. Whatever I had explained in the previous slide, the same thing is being represented here in a much more clearer way, right. So when VGS equal to 0 volts, when VGS is 0, right, ID equal to IDSS, saturation current, okay. So I'll be getting the extreme positive point, and when VGS equal to pinch off, ID equal to 0, okay. So these two are the extreme points in the transfer curve, right. And in between VGS minus 1, minus 2 and minus 3, okay. And please observe the shape of the curve here. It's not a linear one, it's a non-linear one. Alright, okay. So moving next, some important relationships that exist between JFET and a BJT, okay. We cannot call them as similarities, nor they are dissimilarities, but just a comparison between the terms with respect to JFET and BJT, so that it will help us to understand both the devices in a better way, okay. Well, JFET is given by Shockley's equation, okay, and the equation is ID equal to IDSS 1 minus VGS upon VP the whole square. This is a very, very important expression, students, okay. You will have to remember this expression for a JFET. For a BJT, the expression was very simple, right? The collector current is equal to beta times IB, okay. Further, ID equal to IS. In the case of a JFET, ID drain current is equal to the source current. And why is it so? Because gate current will be 0. Yes, okay. So I think we'll have to focus on this point now, considering the symbol of a JFET, okay. So gate, drain and the source. Now VG, and this will be ID, and this is IS, okay. So the equation says drain current equal to source current. Then will there be any gate current here, IG? I am asking students, will there be any gate current? The answer is no. The gate current will be equal to 0, because FET is not a current controlled device, okay. If it would have been current controlled device, then gate current would have flown, similar to the case of BJT. However, FET is a voltage controlled device, and it is the gate voltage that controls the current flow from drain to the source or from source to the drain, okay. So that IG will always be equal to 0. What if IG was not equal to 0? What would have happened? Just a question. What if IG was not equal to 0? Then the device would have damaged. As simple as that, okay. And why is it so? Well, let me just very quickly go back to one of the slides which shows the construction, right. Okay, here itself. See, if here also it is very clearly mentioned IG is equal to 0 amperes. If IG was not equal to 0 amperes, that would have meant that a horizontal current is flowing, okay, through the depletion region, which is wrong, right? Okay, current will never flow through the depletion regions. It only flows from source to the drain, right? Okay, so going by that terms, you will have to understand that the gate current will always be 0. for a JFET. Okay. So similarly, in the case of a BJT, collector current is almost equal to emitter current. Okay, it's not exactly equal, it's almost equal. Why? Because for a transistor, for a BJT, you have base current, you have collector current, and you have emitter current. Okay, well, as per the terminologies, IE should be equal to IB plus IC. But we know that the magnitude of the base current is very small, right? IB is small. If IB is small, then I can say that IE is almost equal to IC. Okay, so because of that we have this expression. Further, base to emitter current in the case of a BJT is 0.7 volts, okay, because it is of silicon diode. Okay, fine. So I think these two diagrams explain a lot. Okay, you have the expressions and you also have the currents and the voltage polarities. Okay, so it's a nice way of representing or differentiating between a JFET and a BJT. All right, so the last topic of this particular session is on specification sheets. Okay, very quickly, we'll try to highlight upon the importance of a specification sheet. Okay, first of all, suppose if we try to purchase any of the electronic devices, it could be online or offline. Generally, along with the devices, we will be given a specification sheet, right? So just write it. Whenever you purchase any device, along with that, you will be given a specification sheet or an information sheet, okay, which actually provides all the necessary information regarding the maximum voltage or the current limitations or even the power limitations, okay, and also with respect to the temperature. So all these information will be provided in the specification sheet. Okay, so just like whenever you purchase any new cell phone, okay, so along with the cell phone you will be getting a charger, plus you will be getting a specification sheet also, okay, wherein most of the information regarding the noise level, voltage things and all will be mentioned. Okay, now the point is, what all information will be present in the specification sheet? Okay, practically speaking, each and everything about that particular device will be mentioned or has to be mentioned in a specification sheet. However, it is not mandatory that as an end user I need to know everything. Okay, it is sufficient for me to know only a few important terms. And what are the few important terms? Well, let's try to look at some of them. Okay, say for example, the maximum ratings is very important, right? Because we need to know what is the maximum drain to source voltage that can be given to a JFET. What is the maximum drain to gate voltage? What is the maximum gate to source voltage? Okay, as you can see it here, it is a value of 25. That means I just cannot blindly give some 100 volts across drain to source terminals of a JFET. Okay, if I give that, the device will get damaged. Okay, I'll have to restrict myself based upon these values, right? Similarly, the maximum current flow that can flow through a JFET will also be limited. Okay, here the forward gate current is approximately 10 milliamps. Okay, it cannot exceed beyond those things. Similarly, the device will operate properly within some certain temperature ranges. Okay, here the operating and storage junction temperature range is from -55 to +150 degree Celsius, right? I just cannot give a temperature of 300 or maybe 400 degree Celsius to a particular JFET and try to get the characteristics out of it. It may not work out, right? Similarly, there are some thermal characteristics. Okay, Further, there are some electrical characteristics, off characteristics and on characteristics. Okay, these are extremely important. Similarly, there are something called as small signal characteristics mentioned in the specification sheet. Well, these are extremely important. Okay, if you want to design an amplifier, okay, an amplifier wherein the input signal will be a sinusoidal one and the frequency of it will be it could be in kilohertz or it could be in megahertz or even sometimes it could be in gigahertz. Okay, so if I consider various frequencies and if I want to design an amplifier, then the circuit designer will have to concentrate on various parameters, and the most important parameters are the transfer conductance, the output conductance, input capacitance, and so many things. Okay, so all these parameters should be carefully taken care of. In the specification sheet, you also be given with the information of the output characteristics, the power dissipation versus ambient temperature, and also other informations related to capacitances, the conductances, transconductance as well as output conductance. Okay, these are just for information purpose. Okay, so interested readers can just go through these things for some more additional information, okay, which will improvise your circuit and as well as the amplifier design knowledge. Okay, and the last point is on the operating region, right? Well, for a proper amplifier design, a normal operating region for linear amplifier design is the region which is in blue color. Okay, so the circuit designers will be taking care of this operating region as well. Okay, based on the user requirements as such. Okay, fine. So all right, so that was all about the construction and the characteristics and some more additional information about JFETs. In the next class or the session, we will be discussing about a much more improvised and an important device when compared to a JFET. It's called as MOSFET. Okay, it stands for metal oxide semiconductor field effect transistor. So we'll be looking at it in our next session. Okay, so students, if you have any doubts, then you can ask me.